As mentioned earlier, in this particular chapter, we will be dealing with polynomials in only a single variable. Now, in this video, let us have a look at the definition of a polynomial in one variable. This right here is the definition of a polynomial in one variable. Now, this might look like a very daunting definition, but let us break down this definition and let us make sense of it. Now, here I have the polynomial in one variable. It simply means that the polynomial must contain only a single variable. It could be x, it could be y, it could be anything, but must be a single variable. Now, polynomials in one variable are algebraic expressions that consist of terms. We learned that before. A polynomial is simply means many terms, so it contains many terms. It could be 1, 2, 3, any number of terms. The terms are to be in the form a x raised to power n, where n is a non-negative, which means positive or zero integer, and a is a real number. Now, this right here is the general form of a term in a polynomial. A is supposed to be a real number. That makes a lot of sense. So a could be anything, any real number. X is the variable, clearly, the single one variable we'll be using in the polynomial. And n is the power of x. Now, we have certain conditions for n, which is that it has to be a non-negative integer, which means it can be either positive or zero, right? And it has to be an integer. Now, apart from this, we've also learned that this number a here, it is the coefficient of the term. We've learned that in the previous videos. The degree of a polynomial in one variable is the largest exponent in the polynomial. That is also something we've learned in the last video. Now let us look at this term right here, non-negative integer, which means either positive integer or zero. This means that n is not supposed to be a fraction because it has to be an integer, right? And neither can nor can n be any negative integer. So n is not allowed to be -2, -3, any sort of a negative number, and also n is not allowed to be any fraction or any decimal, right? Now, why is that so? Why do we not include such numbers in our definition of a polynomial? Well, the simple reason is such polynomials that have terms. For example, I could have a polynomial that has a term 2x raised to power -2, or I could have a polynomial with the term 4x raised to power half. This also means that which equals to 4x. So when we have half a power, it means that we have a root of that particular number. So 4 times root x. Why is this not a polynomial? Why is this, which is the same thing, not a polynomial? And why is this not a polynomial? So also you might know this can also be written as 2 times 1 upon x square, right? When you take the inverse of this, when you reciprocate it, it becomes positive, right? So why are these two not considered as polynomial? Well, the simple answer is the behavior of such polynomials is slightly different from the polynomials that fall under this definition. And just to differentiate between the two, we do not include such such polynomials under the definition of a polynomial. So these are not referred to as polynomials, and they do not fall under the definition of polynomials. They are simple expressions that will be dealt in further classes, and these are not the subject matter of the current chapter. Now let us have a look at a few terms that qualify as polynomials. For example, 2 times x cube. 2 is a real number, 3 is a non-negative integer. Therefore, this is a polynomial, right? This term will be qualified as a polynomial. So if this is a part of any polynomial, it will fall under this definition of a polynomial. -5x square, -5 is a real number, 2 is a non-negative integer. Therefore, this is also a polynomial. Half times x raised by 1. Now, half, this is the coefficient, and a coefficient has to be a real number. Half is a real number. Therefore, this is a polynomial, right? 1 is a non-negative integer. Therefore, this is a polynomial. 0 0.1 times x raised to the power 10. 10 is a non-negative integer. 0 0.1 is a real number. Therefore, even this is a polynomial. Lastly, we have root 2 times x raised to the power 0. Now, is this a polynomial? Well, root 2 is a real number, right? It is an irrational number, but irrational numbers are real numbers, right? Therefore, this is a real number, the coefficient is a real number, and the power 0 is a non-negative integer. It can be 0. Therefore, even this qualifies to be called as a polynomial. So all these terms written down here, they can be part of a polynomial, and that particular expression will be a polynomial. Let us have a look at another example of a polynomial. This is a complete polynomial right here. Is this so this expression right here, is this a polynomial? Well, let us look term by term. This term, real number, non-negative integer, perfect. So this term is fine. The next term, minus 4. Is minus 4 a real number? Yes. Is 5 a non-negative integer? Yes. So this term also qualifies. Root 3, it's a real number. 1 is a non-negative integer. Therefore, even this term qualifies to be called a polynomial, and therefore this whole expression is a polynomial. Perfect. Next, we have this example. Is this expression a polynomial? Well, 0 0.3 is a real number. 0 is a non-negative integer. So this term qualifies. Minus 1 is a real number. Minus 2, is that a non-negative integer? No. So we have a problem right here in this term. So this term does not qualify. Next term, plus 1, it's a real number. 0 0.5, is that a non-negative integer? Well, it is non-negative, but is it an integer? No. So even this does not qualify, and therefore, because we have certain things that do not qualify as that do not fall into this definition, therefore this whole expression is not a polynomial. Therefore, this is the definition of a polynomial in one variable, and now onwards, whenever I refer to the term polynomial, I would be referring to this whole expression polynomial in one variable.